The bomb that could see. How precision guidance ended fortress warfare. 32 seconds. The weapon fell through scattered clouds at 600 miles per hour, its nose cone pitched downward, 4 control fins making microsecond adjustments to keep it centered on a beam of invisible light. Inside the bunker 18 feet underground, General Nguyễn Văn Thọ signed a supply requisition, surrounded by 6 feet of Soviet-certified reinforced concrete. He had 11 minutes left to live. This is the story of how a laboratory concept transformed warfare forever, told through 3 parallel threads: an engineer's obsession, a general's miscalculation, and 32 seconds of guided flight that made fortresses obsolete. The problem: bombs that couldn't see. Weldon Word sat in his laboratory at Eglin Air Force Base in 1965, confronting a problem as old as aerial warfare itself. Bombs were blind. Once released from an aircraft at 20,000 feet, they became slaves to gravity and wind, ballistic projectiles with no way to correct their course as crosswinds pushed them off target. The statistics were damning. Conventional bombing offered perhaps a 3% chance of hitting a small, hardened structure under ideal conditions. The Air Force had tried everything: better bomb sights, computerized release systems, even nuclear weapons large enough that accuracy didn't matter. Nothing worked against small, hardened targets buried under jungle canopy. Word had a radical idea. What if the bomb could see? The concept wasn't entirely new. Germans had experimented with radio-guided bombs during World War II, but radio signals could be jammed. Word thought about light instead, specifically laser light. A laser beam could illuminate a target with concentrated energy at a specific wavelength. Sensors on a falling bomb could detect that reflected light and steer toward it. Simple in theory, brutally difficult in practice. The engineering nightmare. A bomb falling at 600 miles per hour had maybe 30 seconds from release to impact. The guidance system needed to detect laser light, calculate position relative to the target, and adjust flight surfaces, all while spinning, vibrating, and experiencing forces that would crush most electronics. Word's team built prototype sensors that shattered on release. They designed control fins that couldn't move fast enough. They tested laser designators that lost target lock when smoke drifted through the beam. Texas Instruments won the contract to build the actual hardware in 1968, but the development process nearly killed the entire program twice. 4 components, infinite problems. The Payway 2 system used 4 components: a laser seeker in the bomb's nose, control fins mounted on the front section, guidance electronics, and a battery pack. The complete guidance package weighed 30 pounds when attached to a standard Wark 82 500-pound bomb. The Air Force wanted 20 pounds. Engineering teams argued that physics didn't care what the Air Force wanted. The laser seeker contained a 4-quadrant detector that measured reflected laser energy. When the bomb drifted left of the laser beam, the left quadrants received stronger signals. Electronics interpreted that imbalance and commanded the control fins to steer right. The system updated 100 times per second, making constant tiny corrections as the weapon fell. But Vietnam's humid climate threatened to blind the entire concept. Laser light at 1.06 microns, the wavelength used by military designators, scattered in humid air like fog diffusing headlights. Southeast Asian humidity exceeded calculated scatter coefficients by 40%. The control fins created their own nightmare. Mounted near the bomb's center of gravity for maximum steering authority, they generated turbulence that destabilized the weapon at certain speeds. Engineers redesigned the fin geometry 17 times, adding small vanes to manage airflow, adjusting angles of attack. Each modification required new test drops, new data analysis, new arguments with Air Force officers who demanded immediate results. Then came the electronics challenge. Transistor circuits in 1971 weren't robust. A bomb experienced 20 Gs of acceleration at release, then vibration from supersonic airflow, then massive deceleration forces at impact. Early prototypes had circuit boards that cracked on release. Solder joints failed. Engineers redesigned the entire electronics package 3 times, eventually settling on individually potted components mounted on shock-absorbing frames. Battery technology became the limiting factor. The guidance system needed power for 30 seconds maximum, but batteries capable of delivering sufficient current were either too heavy or too unreliable. The final design used thermal batteries that activated on release, generating power through chemical reactions triggered by the weapon's acceleration. They worked once, produced exactly what the system needed, then died. Perfect for a bomb that only had to function for half a minute. By early 1970s, the Payway 2 had achieved 60-foot accuracy in combat testing, a revolutionary improvement over conventional weapons, which measured accuracy in hundreds of yards. The weapon worked. Now it needed a target worth the technology. The fortress. Soviet certainty. General Nguyễn Văn Thọ selected his command post location using Soviet doctrine refined over 2 decades of bunker construction. The bunker sat 18 feet underground, reinforcing with steel rebar according to specifications that had protected command centers from Berlin to Pyongyang. Soviet military advisors had done the calculations themselves. The thickness of the ceiling alone, 6 feet of solid concrete, could absorb a direct hit from any weapon in the American arsenal. The bunker's ventilation system drew air through filtered shafts disguised as termite mounts. Communication lines ran underground for 200 meters before surfacing. Supply trucks arrived only at night, following routes that changed weekly. The location, 30 miles northwest of Thong Ha, placed the bunker beyond the effective range of most tactical aircraft. Triple canopy rainforest made visual identification nearly impossible from the air. American fighter bombers had to fight their way through the heaviest anti-aircraft defenses in military history just to reach this sector. General Thọ had earned his reputation fighting the French at Dien Bien Phu, where artillery hidden in caves had destroyed an entire airborne garrison. He applied those same principles here: concealment, depth, and overhead protection. The mathematics favored defense. A single bomb falling from 20,000 feet covered maybe 50 square meters, a pinpoint against the vastness of jungle terrain. Hitting a specific building required either incredible luck or dozens of aircraft dropping hundreds of bombs. Neither approach worked against a target this well protected. Soviet advisors had designed dozens of these command centers throughout North Vietnam, each one a miniature fortress built to withstand sustained aerial bombardment. They'd studied American tactics in Korea, where carpet bombing had reduced entire cities to rubble, but failed to eliminate hardened targets. Inside the bunker, electric lights illuminated maps showing friendly positions across 3 provinces. Radio operators maintained contact with artillery batteries and supply columns. The general staff planned next week's operations while filing clerks organized intelligence summaries in metal cannons bolted to concrete walls. Nobody wore helmets, nobody rushed. The routine of military bureaucracy continued undisturbed by the distant rumble of American aircraft dropping their payloads uselessly into empty jungle. The general's operational security measures were excellent, but they contained a fatal flaw he couldn't have anticipated.
The weakness. Eyes in space. What General Thọ didn't account for was orbital reconnaissance. American KH-9 satellites photographed North Vietnam from 100 miles up, their cameras resolving objects as small as 2 feet across. Photo interpreters at the National Reconnaissance Office studied thousands of images, looking for patterns. The command bunker itself remained invisible under triple canopy forest, but the supporting infrastructure gave it away. Analysts noticed supply convoys converging on a specific grid coordinate northwest of Thong Ha. Trucks arrived at night, but infrared sensors detected their heat signatures. Communications intercepts revealed radio traffic originating from the same location. Over 3 months of observation, intelligence officers built a pattern of life analysis showing regular vehicle movements, consistent power generation, and protected communications, all indicators of a high-value command facility. The general's operational security actually worked against him. By restricting vehicle access to a single concealed road, he created a detectable pattern. Supply trucks traveling to nowhere attracted attention. Satellite photos showed tire tracks appearing at the forest edge, then disappearing under vegetation, then reappearing at the same spot days later. Photo interpreters marked the location as a probable headquarters facility. Intelligence summaries rated it high priority. Soviet advisors had designed the bunker's overhead protection against vertical threats, bombs falling straight down from high altitude. The 6-foot concrete ceiling could absorb tremendous kinetic energy distributed across a wide impact area. But the engineering calculations assumed conventional weapons with circular error probables measured in hundreds of feet. The Soviets had built a fortress against inaccurate bombing, never imagining that American technology would soon eliminate inaccuracy as a defensive advantage. 30 miles away, Air Force intelligence officers briefed F-4 Phantom crews on a target designated Structure 57, a suspected command facility whose exact location had been verified by multiple satellite passes. Weapon loads called for something new: GBU-10 Paveway 2 laser-guided bombs, each one a 2,000-pound Mark 84 fitted with a guidance kit that had never been used against a target this heavily defended. May 23, 1972, the mission. The mission briefing at Ubon Royal Thai Air Force Base began at 600 hours. Intelligence officers spread reconnaissance photos across the briefing table, black and white satellite imagery showing jungle canopy with a single notation, Structure 57, suspected command facility. The photos revealed nothing visible on the ground, just trees and shadows. But analysts had marked a precise grid coordinate based on 3 months of traffic pattern analysis. Captain Lin Hill and his weapons systems officers studied the target coordinates. Their F-4D Phantom would carry 2 GBU-10 Paveway 2 bombs, 2,000-pounders fitted with laser guidance kits.
Total weapon weight per bomb, 2,250 pounds, which meant reduced fuel load and limited loader time over target. The mission profile called for a single pass. Get in, designate, release, get out, no second chances. The laser designator posed its own complications. The pave knife pod mounted under the Phantom's fuselage contained targeting optics and a neodymium-doped yttrium aluminum garnet laser that pulsed at 10 Hz. The weapons systems officer would acquire the target visually through the pod's television camera, lock the laser onto the aim point, and hold designation while the bomb fell. 30 seconds of continuous laser illumination while flying through anti-aircraft fire. Fighter pilots called it hanging your ass out. Anti-aircraft defenses around Tonghua included 67 known gun positions and 14 surface-to-air missile sites. Hill's wingmen would carry conventional Mark 82 bombs for suppression, essentially bait to draw anti-aircraft fire while the lead aircraft designated the primary target. The briefing ended with timing coordinates: wheels up at 7:45, target time on target 8:47. Weather window closed at 9 a.m. when forecast clouds would obscure the area. One shot at a target they couldn't see, defended by weapons designed to kill aircraft, using a guidance system that had never struck a bunker this hardened. Hill signed the mission roster and walked to his aircraft.
32 seconds. The strike. The F-4 Phantom crossed into North Vietnamese airspace at 08:41 hours, flying at 22,000 feet through scattered clouds that turned the jungle below into patches of green and shadow. Captain Hill's weapons systems officer activated the pave knife targeting pod, and the television display flickered to life, showing a grainy black and white image of terrain sliding past at 7 miles per minute. He adjusted the pod's gimbal, slewing the crosshairs toward the coordinates marked on his kneeboard card. The grid reference pointed to dense canopy with no visible structures, exactly as the reconnaissance photos had shown. 3 miles ahead, the wingman's F-4 rolled inverted and pulled through into a 45-degree dive. Conventional Mark 82 bombs tumbled away from the wings, falling toward the jungle in a pattern meant to provoke anti-aircraft response. 4 seconds later, tracers erupted from concealed gun positions. 37mm shells walked across the sky in streams of orange light. The wingman broke hard left, afterburners igniting as he clawed for altitude through a sky suddenly filled with exploding metal. Hill held his approach steady. In the rear cockpit, the weapons systems officer centered the targeting pod crosshairs on a slight discoloration in the jungle canopy. Maybe a building, maybe just different vegetation. Impossible to tell at this range. He locked the laser designator and felt the pod's tracking system engage. A small circle appeared on his display, indicating the laser was painting the target with 10 pulses per second of invisible infrared light. Each pulse lasted 14 nanoseconds. Each one bounced off whatever sat beneath that canopy and reflected back toward the sky. The weapons release computer counted down altitude and airspeed, calculating the precise millisecond when aerodynamic forces would carry the GBU-10 from aircraft to target. The release tone sounded. Hill pressed the pickle button. 2,000 pounds of bomb and guidance kit dropped away from the centerline station, immediately pitching nose down as the control fins bit into the airstream. The payway seeker head came alive, its 4-quadrant detector scanning for reflected laser energy at 1.6 microns. The bomb found the reflected light immediately, a cone of infrared energy bouncing off the target below, and commanded the control fins to steer toward maximum signal strength. Anti-aircraft fire shifted toward Hill's aircraft. The Phantom shuddered as 57mm shells detonated close enough to rock the airframe. Hill held course. In the rear seat, the weapons systems officer watched the targeting display, keeping the laser crosshairs centered on that faint discoloration in the canopy. The bomb was falling at terminal velocity now, accelerating through 600 miles per hour as gravity and aerodynamics pulled it earthward. 20 seconds after release, the GBU-10 was still tracking, its control fins deflecting microscopically, making constant corrections as crosswinds pushed the weapon off course. The guidance system responded 100 times per second, always steering toward the brightest reflected laser light. At 10 seconds before impact, the bomb penetrated the clouds that had been threatening to block designation. The seeker never lost lock. The laser beam remained steady. Inside the bunker, General Nguyễn Văn Thọ was signing a supply requisition. Impact. When physics meets certainty. 2,000 pounds of steel and high explosive punched through 6 feet of reinforced concrete at 900 feet per second. The weapon's kinetic energy alone, independent of its explosive content, exceeded anything Soviet engineers had calculated into their protection formulas. At impact velocity of 940 feet per second, 2,000 pounds of steel casing carried kinetic energy equivalent to a fully loaded semi-truck hitting a wall at 200 miles per hour, except concentrated into a cross-sectional area of less than 1 square foot. Soviet engineers had designed the bunker roof to distribute blast force from conventional bombs across wide impact areas. They'd calculated stress loads for weapons that exploded on contact, transferring energy through expanding gas and shock waves. They'd never considered a guided weapon delivering focused kinetic penetration. The weapon's hardened nose cone punched through the first 3 feet of concrete before deceleration forces became significant. The bomb's casing compressed as layers of steel crumpled against reinforced aggregate. Rebar bent and snapped.
Concrete pulverized into powder. The weapon's momentum carried it through another 2 feet of barrier material before physics finally arrested the forward motion. Then the explosive filler detonated. 945 pounds of tritonol, a mixture of TNT and aluminum powder, converted from solid to gas in less than a millisecond. The explosion generated pressure exceeding 300,000 pounds per square inch at the detonation point. That pressure wave, constrained by surrounding concrete and unable to expand spherically, channeled downward through the hole the bomb had already created. The bunker's roof didn't just crack, it fragmented. Chunks of concrete weighing hundreds of pounds blasted into the interior space, accelerated by explosive force that had nowhere else to go. The bunker's interior volume worked against its occupants. Soviet design doctrine called for central supporting pillars that would prevent progressive collapse if the roof was damaged. Those pillars, spaced every 15 feet, meant the explosion's pressure wave bounced off vertical surfaces and reinforced itself through acoustic focusing. The blast pressure that might have dissipated in an open space instead reflected multiple times, creating overpressure zones that exceeded 50 pounds per square inch, 5 times the threshold for fatal lung damage. General Nguyễn Văn Thọ died instantly, along with 4 Soviet military advisors and 17 staff officers. The bunker's electrical system failed as the blast severed power lines. Emergency lighting activated for 3 seconds before secondary explosions from stored ammunition destroyed the battery backup. Radio equipment shattered. Filing cabinets toppled. Maps that had been spat across planning tables burst into flame from the thermal pulse. The ventilation system that had been designed to filter out chemical weapons became a conduit for overpressure. Blast waves traveled through the air shafts, emerging at distant ventilation points with enough force to scatter camouflage netting and send debris 30 feet into the surrounding jungle. North Vietnamese troops stationed 200 meters felt the ground shake. They ran toward the bunker entrance, then stopped when they saw smoke pouring from ventilation shafts that had been hidden beneath fake termite mounds. The bunker's structural integrity collapsed over the next 40 seconds. Supporting pillars that had been cracked by the initial blast couldn't support the weight of fractured concrete above them. Progressive failure propagated through the structure as each pillar gave way and transferred load to adjacent supports. The ceiling came down in sections, burying equipment, bodies, and classified documents under tons of rubble. Above ground, Captain Hill's F-4 Phantom was already 15 miles away, racing back toward Thai airspace with the weapons systems officer still wondering if they'd hit anything. The jungle canopy showed no visible change, no secondary explosions, no smoke plume, just trees and shadows. For now, Hill and his crew had only the certainty that the bomb had guided properly, and the hope that intelligence had identified the right target.
The aftermath, when certainty dies. The first report reached Soviet military headquarters in Hanoi 90 minutes after the strike. A communications officer, face covered in concrete dust, had climbed out of a secondary bunker and radioed that Structure 57 had been destroyed by what appeared to be a direct hit. The message included casualty numbers: 4 Soviet advisors confirmed dead, along with a North Vietnamese general and his entire staff. Soviet officers in Hanoi immediately demanded clarification. A direct hit on a hardened bunker under triple canopy concealment? The probability of such an event approached 0. Then came the damage assessment. A Soviet engineering team reached the site that evening and found the bunker's 6-foot concrete roof penetrated by a single point of impact, not cratered by near-miss explosions, not damaged by fragmentation from multiple weapons. One hole punched straight through Soviet-certified reinforced concrete, with structural failure radiating outward from that single penetration. The engineering team took measurements and photographs, then sent an urgent cable to Moscow. American aircraft had achieved precision strike capability that violated every assumption underlying Soviet bunker defense doctrine. The revolution. Fortresses become tombs. The implications cascaded through Soviet military planning. Every hardened command post from East Germany to North Vietnam had been designed around the same mathematics: thick concrete roofs, overhead concealment, and the statistical improbability of accurate bombing. Those assumptions had survived World War II in Korea. They'd been validated by thousands of American bombing missions that had destroyed vast areas without eliminating specific hardened targets. Now that calculation was obsolete. Soviet intelligence officers reviewed American bombing patterns from previous months and noticed a trend: an increasing number of pinpoint strikes against bridges, power plants, and storage facilities. Targets that had previously required dozens of aircraft and hundreds of bombs were now being destroyed by single aircraft dropping 1 or 2 weapons. The Americans had developed a guidance system that worked in combat conditions. Soviet military journals had mentioned laser-guided weapons as early as 1968, but the articles dismissed them as impractical for battlefield use. Laser beams scattered in atmospheric moisture. Guidance systems couldn't survive the vibration and acceleration of bomb release. Electronic components weren't reliable enough. The theoretical problem seemed insurmountable. Except now a Soviet-built bunker sat collapsed in the Vietnamese jungle, penetrated by a weapon that had defied those theoretical limitations. The strategic implications terrified Soviet planners. The entire defensive architecture of the Warsaw Pact depended on hardened command bunkers that could survive NATO airstrikes long enough to coordinate counterattacks.
Those bunkers represented billions of rubles in construction costs and decades of engineering refinement. If American aircraft could now destroy them with single bombs, Soviet forces would lose command and control capability within hours of any war's opening. The bunker at Tongha wasn't just a tactical loss, it was proof that Soviet defensive doctrine had become obsolete overnight. Moscow ordered immediate research into countermeasures. Could laser beams be jammed? Could smoke screens block designation? Could bunkers be hardened further? But the fundamental problem remained. If Americans could guide weapons within meters of any target they could see, no amount of concrete would guarantee protection. The age of the fortress had ended, killed by a guidance system that turned falling bombs into Hunton projectiles that followed reflected light to their targets. The numbers. Victory through physics. Between 1972 and 1973, American aircraft dropped 28,000 laser-guided bombs in Vietnam, with a circular error probable of 60 feet. That meant half of all weapons landed within 60 feet of their aim point, compared to conventional weapons that achieved 3% accuracy under ideal conditions. Bridges that had survived hundreds of bombing missions fell to single payway strikes. Power plants went dark after one aircraft pass. Storage facilities that required squadron-level attacks now disappeared under individual bombs that followed laser light through smoke and weather to strike exactly where designators pointed them. Weldon Word's concept, a bomb that could see, had transformed from laboratory theory to battlefield dominance in 7 years. The engineering problems that nearly killed the program 17 times had been solved through incremental refinement, stronger seeker heads, redesigned control fins, thermal batteries, potted electronics that survived combat stress. Texas Instruments delivered a guidance kit that weighed 30 pounds, cost $3,000 per unit in $1972, and could be bolted onto standard bombs already in inventory. No specialized aircraft required, no exotic infrastructure, just a laser designator, a weapon with a seeker head, and crews trained to hold target lock for 30 seconds. The legacy. Wars transformed. The strategic impact exceeded anything Air Force planners had predicted. Soviet bunker doctrine, refined since World War II, assumed that hardened targets could survive sustained aerial bombing because accuracy remained the limiting factor. Thick concrete roofs protected against near misses, deep burial protected against blast overpressure, concealment made targeting difficult. Those advantages all disappeared when weapons could guide themselves to within feet of designated points. The mathematics of fortress defense collapsed when circular error probable dropped from hundreds of yards to tens of feet. NATO immediately accelerated laser-guided weapon development. The Soviet Union initiated crash programs to harden existing bunkers and develop countermeasures against laser designation. Neither response addressed the fundamental shift. Precision guidance had made static defenses vulnerable. The tactical revolution that began with Weldon Word's laboratory experiments at Eglin Air Force Base propagated through military doctrine worldwide. Wars would no longer be won by carpet bombings or artillery barrages that traded massive resource expenditure for modest accuracy. Future conflicts would feature precision strikes where individual weapons destroyed specific targets that commanders could see and designate. The Vietnam War ended in 1973, but laser-guided weapons defined every conflict that followed. Israeli aircraft used American-supplied payways to destroy Syrian air defense systems in 1982. NATO forces employed precision weapons to dismantle Iraqi infrastructure in 1991. By 2003, GPS-guided bombs had supplemented laser guidance, achieving accuracies measured in feet rather than yards. The progression from Weldon Word's initial concept to modern precision strike capability took 40 years, but the fundamental principle remained unchanged. Guidance transforms falling ordnance from area weapons into point weapons. Conclusion. The death of mathematical certainty. General Nguyễn Văn Thọ died because he trusted engineering calculations that assumed weapons would remain inaccurate. Soviet advisors designed his bunker using mathematics that had protected fortresses since concrete and steel replaced stone and timber. Those calculations were correct for the weapons that existed in 1968. They became fatally wrong when payway guidance kits turned dumb bombs into guided projectiles in 1972. The revolution happened not through exotic technology, but through applied physics. Seeker heads detecting reflected laser light, control fins steering toward maximum signal strength, and weapons following invisible beams to targets their crews never saw with naked eyes. Weldon Word's laboratory work at Eglin Air Force Base killed fortress warfare. The bunker that collapsed at Tongha on May 23, 1972, represented the last generation of command posts built on the assumption that overhead protection guaranteed survival. Precision guidance made that assumption obsolete. In 32 seconds of guided flight, a 2,000-pound bomb following a beam of invisible light demonstrated that no fortress could survive when weapons learned to see. The age of static defense ended not with a whimper, but with a single, precisely aimed explosion that shattered mathematical certainty and changed warfare forever.